This is a 1959 Gibsonette GA-8. This is a 6v6 dual 6v6 Class A amplifier. Inside, there were no modifications made. It hadn't been touched at all. However, the components were really bad. The fuse was covered with aluminum foil to allow it to short out. All the tubes tested good except for one 6v6, as well as the 12AX7, which is extremely microphonic. The electrolytic capacitors were in a terrible state. They had burned through, one had burned through the other. It was really bad. And this was definitely going to be a job that was going to require a lot of electrolytic recapping in order for this amplifier to ever work again. As a point of reference, we're going to look at this 0.02 microfarad capacitor, which is the same type of capacitor with regard to construction as the one that we find in this 1959 Gibsonette, right? This is an Astron made in New Jersey, and this is reading 0.22. This one right here and that one right there. They're both 0.22 microfarad, 0.022, excuse me. But what we're going to do is we're going to hook up to this, and I've already taken readings, and I'm not going to bore you with the readings. This one is 0.03, so as far as capacitance goes, it's absolutely fine. Okay, this one reads 0.023, so this one is closer, but still within tolerance. The important thing is the leakage of these, right? So I'm going to plug this one in first, right? And we're going to go straight off this board here into the IT11, right? So we're connected there. We got our IT11 up right now, and I got it down to 3 volts, and I'm going to set it to leakage. Okay, so it's 3, 6, 9. That was 10. That's 15, 25, 50 volts, 100 volts, 150, 200. You can see it takes longer to charge, but everything's fine. 200, 250. There's 300 volts going through here. 350 volts. And finally, that's 400 volts DC going through this capacitor. And this is on the lowest paper mica setting. This is measuring microamps, right? So that is showing good. So let me safely discharge this capacitor, right? So this capacitor is discharging. I'm going to remove it right now from this cap and hook it to this this Astron right here. And I disconnected one end of this capacitor, so it's definitely not in circuit. All the current must pass through this capacitor from the red side, from the positive, to make its way to the black side, because as you can see, I've opened up that red side, right? And we're going to dial this back all the way to 3 volts, right? And we're going to hit leakage, right? And there's 3 volts, 6, 10, 15, so 25, slow down a bit, right? There you go, somewhere between 25 and 50. This capacitor is no longer acting as a capacitor, it's acting as a resistor, right? So this one is rated, according to the rating on the side, is 400 volts DC. If I look at the actual schematic, what it's seeing is in and around 160 volts. Well, that's fine, right? So the capacitor is rated above the maximum voltage of the circuit. But somewhere between 25 and 50 volts, this thing is already garbage. It's a resistor in circuit, and it's no good. So it's got to be replaced. That can't work in there. If I'm not going to clear, if it was getting like 200 volts, maybe 220, and then cutting out, I would say fine, whatever. But we're not even making it near there. So the capacitor is junk. The other coupling capacitor seems good. It measures 0.025 microfarads. ESR is somewhat higher, but it's really hard to judge what the ESR would be for this type of capacitor in this configuration. I'm not really concerned about that. The most important thing about this coupling capacitor is obviously the capacitance and the leakage, the DC leakage. So now I got this one I disconnected here, so I'll be able to test it out as circuit and I'm set up with the same exact scenario here. I got it down to 3 volts, and you can watch, this is current limiting if you don't know, so the more voltage, it takes longer to charge a capacitor. So we go 3, 6, 10, 15, 25, see 50 work, it already passed the other capacitor, 100, 150, 200, 250, 300, 350, 400. So as it turns out, let me just discharge that. So as it turns out, this capacitor is good and this one is bad. I still have to test some of the others. Obviously the electrolytics are garbage. The top one here actually has a hole burned through it out the other side, and one of the leads inside is actually shorted to ground. So we pulled out the large electrolytic filter capacitors so we could take some measurements with regard to the diameter. I was able to source some firecracker style ones like this. They're 10 by 10s, so we're going to do 2 10 by 10s, and then we're going to parallel another 10 on there to get the 10 by 20 for the one down there. In other investigation, I have pulled off this connector for this 500 picofarad capacitor. I didn't anticipate that there'd be any major issue with this one. I tested it up to 6 volts, right? And it tested good, so we're going to call that a good capacitor. And just to show you, because I usually don't use this as my capacitor tester, but I happen to have it on there, right? Set to picofarad, right? And I'm going to roll this up, and as I approach 5 over here, we'll see that it starts to open up right there. You can see it bounces back. So we just try and find where the middle of that bounce is on this piece of test equipment. Where we have the greatest open, and it turns out it's, you know, around 5. I measured, what did I measure? Just around 490 something on the modern tester. So that capacitor is good. I'm going to test that 47 while I'm down there. While I got this removed, I got room to work. I've disconnected this capacitor right here. This is a 6 volt. This is a 6 volt capacitor, and this one will be checked next. This is a 20 microfarad. So if we have a problem with that, we will replace that as well. I want to check these very last things before I put in the order. So that's what we got. This 20 microfarad capacitor is reading nothing at all. I could get some straight capacitance. I see it's showing a negative in it. That usually tells me bad things, that it might be more inductive than anything at this point. So there's no reason to further test this. I tested it on 2 separate devices. I can't get an ESR reading. The ESR reads this one to be open. So this one is going to be replaced too. This is a very interesting one, that this one should go bad too as well, because this capacitor is over here. I'm sorry. You know, this sets the stage for the response on this particular 12AX7 circuit right here. So what you basically have is an open and a 1500 ohm resistor. I haven't computed what that would do to the frequency response, but that obviously can't be good, you know. So we're going to replace that one as well. So we found that one is bad. That one is bad. Both of these are bad. You can see the fire burned a hole through this one, and then it actually burned that one as well. This one is good, as we would expect. It says between the tone controls, doesn't see a whole lot of action, and it's very low capacitance. And then I got that 47 to test back there. So a lot to replace on here as far as capacitors go. Resistors, I'm seeing just one that's a little out of tolerance. That's a 220 reading 264. So that'll go. It's just a resistor. It's not really that important. I got this one bumblebee down there that needs to be checked. That comes straight off the power line. It's a 0.022, but that's for the power switch. That's not for any circuit in here. So that'll have to be checked, and then that should be good. That'll stay, and I'm not going to worry about it. And then we'll order new parts to get this buttoned up. I rarely have any issue with these little ceramic ones. I've disconnected this one here. This is a 0.0047 microfarad, and it is exactly what it is. We're not going to test any further. I'm going to reconnect it back to the pot. We're going to call that good. So both of those in between the pots are good, as we expected. The next thing I'd like to check is the audio output transformer. This is the GA-8 from Gibson, and from the information that I gathered from them, the winding ratio is supposed to be 27.5 to 1. So while I did test this, the input and output, the primary and secondary windings of this coil, with a continuity tester, I wanted to make sure that everything's running right by being able to replicate the ratio that was in the documentation. So what I've done is I have a AC multimeter right here, and this is reading the secondary winding, which is 0, it's just a little bit off. And this one is reading the primary winding. And I'm going to use this signal generator to generate this AC waveform. And by looking at the AC waveform, we're going to check, first of all, if it's linear, which we would expect, that the ratio between this one and this one would be the same. And we're also going to check, based on that ratio, what the winding ratio is, right? So right now I have it off. And one of the reasons I'm doing this primary concern was this particular capacitor. This isn't the one that burned, believe it or not. The fire shot through this one over here, this pinhole, and then took out this capacitor with it. So I always have a concern about these transformers. So let's get started. We're going to bump up the voltage till we get to 1/8 of a volt here, 0.125, right? So we're going to bump this up to 0.125, and then we're going to look at the output right here. So let's go ahead and start cranking this up. So there we have 1/8 of a volt. And if we look at the other side, we'll see that we see around 3.4 volts, 3.4 volts on the output. So I'll record those. And then what I'm going to do is I'm going to double this to 1/4 of a volt, and we should see about 6.8 on this side. So let's do that now. So now I have 1/4 of a volt, and we see that it did double. It went from 3.44 to 6.88. And by taking those values, and I have some other values that I rounded before, you could see they're just about the same right there. What I ended up with was, by multiplying 1/4 by 4 to get 1, and then obviously 6.88 by 4, I ended up with 1 to 27.5. And as it turns out, from the information provided, it is in fact 27.5. So now that we have that information, knowing that the speaker is measured at 3.5 ohms in and around, I used resistance to measure it. Obviously it's going to be off slightly, right? But just to get a ballpark here, what I did is I took the Z, which is the ratio squared, right? 27.5 times 27.5, and I ended up with 756.25. I then multiplied that by the speaker resistance and ended up with 2,647 ohms. If you look at the recommended values for the plate resistance for a 6v6, you will find that it is 5,000 ohms. However, because this one is a single-ended Class A with two 6v6s, we go and double that value. So 2647 becomes roughly around 5,000 ohms, which is exactly what we're looking for to drive this amplifier in this configuration. So we're going to say that that is good. I like to use Mr. Carlson's method to determine the outer foil of the capacitors before I replace them. I imagine that these Astrons probably have this line on the side to indicate the outer foil. Even though they don't have a polarity per se, they do have a shield, right? So the problem is with the replacement capacitors, they're really so sensitive that there is no way to really tell by using the method with your fingers. So what I did was I turned up a function generator, some high frequency, 4,000 kilohertz, something like that. And what I did was I set it up here, and then I just take the red to see how much interference is generated as I bring the red closer. And you can see that if I lay it on there, you see the interference increase, and then it comes back to normal, right? So that's the red. You see, that's what I'm doing. All right, now let's flip it around, which is not easy to do with the camera. We'll try. Okay, so we got it flipped around, and now we'll look at it again. And from this we can tell, based on the height of the interference that's produced, which side is the shield. So here it is, everything's done. Everything's all wired in. Everything that needed replacing was replaced. Like I mentioned, these only come in 1010s and not 1020. So I have a 10 in parallel down there. It's the only modification. And it's not really an electrical modification. It's just a, it's a matter of being able to source parts. So I checked the heater voltages and everything before putting in the rectifier. Checked that operation was good. Obviously, the heater voltage was a bit high. All the voltages were a bit high because this is expecting a load from the rectifier, which was not getting to supply the B+ rails. So we saw 748 coming in AC to where the rectifier would be. And on the output for the rectifier, we have 5 volts and 748 volts, along with a heater of 7.14. So now we're going to do some testing. We're going to fire it up with the rectifier. We're going to check the B+. I want to point out that I have these 8 ohm dummy loads. And this is a 4 ohm system, so it's really easy. These are 8 ohms at 100 watts for short couple minute bursts. So what I did was I just wired them in parallel, and now I have 4 ohms at 200 watts, which this will never produce. So this is the perfect dummy load setup for this. So we'll get started on testing. When I test these voltages, I do not do it while making a movie. It's simply too dangerous. So I'll test the voltages and report back. So I've measured all the voltages. Everything seems pretty good. They're all a little bit high, but that's always understandable because these were designed for lower voltages back then, these transformers. They weren't expecting 123 volts on the line. The only problem was I got a voltage drop a little bit too far here. This one's a little bit out of spec. That should be 240. It's reading 227. And this is the voltage dropping resistor right here. And you can see that resistor has gone a bit high. So we're going to swap that resistor out. Everything else based on the statistics seems to match up, or based on the conversion for voltage. So we're going to call this good. I've got to connect it to my dummy load. And what I'm going to do is going to connect it to the oscilloscope to see if I could see any latent hum that's caught in here. I'll probably short the inputs, which is fine because, like I said, it's going into a dummy load. There's no volume anyway. That could eat easily 200 watts of power. That's what we'll do next. Initially, I had seen a waveform on the output here, and I looked at it and I immediately saw, not to get too worried, it was 60 hertz, which means that it wasn't coming from the rectifier. It was actually coming from the input itself. And what I had realized was that as I was working on the amp, I had forgot to push the mains lines back around to the top here, so it was sitting right on top of the rectifier tube. So simply just repositioning those brought it down to 0 hum. So there's no hum. Whether it's a hi-fi amp or a guitar amp, I just bumped into it. Nobody wants line hum injected into their amplifier. That much is for sure. Another problem you face is microphonics, such as this 12AX7, which, as far as readings go, is fine. But what I like to do is just give it a little tap with a pencil, very lightly. And you can see that this tube does have some noise, when you tap it. This one, no problem. That one, no problem, and that's the rectifier. But this one here, a little noisy. You'd probably benefit from swapping it out. We'll see what happens. try it out. Start with, let me bring the tone all the way down. Start with A minor, or C to C. It's got a nice sound. Now I'm going to turn the tone, hold it. Do it again. There you go. You got both pickups on? Go around front, see what it sounds like. Sounds good.